Hello everyone. Many students have been asking doubt in this question, like not able to solve. So I thought of making a video. Those who have not seen this question, please go through it. It's a very nice question. Try to attempt it. If not able to do, then you can go through the solution. Let me start the solution here. So we have been given this surface, which is kind of an imaginary surface. It's a spherical surface of radius r, and there is a point charge q. Now we have to find out the average value of electric field on the surface of the sphere due to this point charge q. Or we can say that if the charge is kept at point q, find out the average electric field at this location. Or if the point charge is kept at p, find out the average value of electric field. Now first of all, many students will be having doubt in what is the meaning of average electric field. So let me tell you a little bit about it. So electric field is a vector quantity. So let's say we discuss about the 1D electric field. Let's say that electric field is some E naught into x square by a square j cap. So this is the electric field which is in this j direction. Now someone asks, okay, this is a variable electric field, it is changing along the x. So find out this average value in the region 0 to 2a. So what we'll do is, to calculate the average, we will divide the entire length into small parts. We'll take one such part at a distance x and of thickness dx. Now how much electric field is present at this location? So the electric field present is E naught x square by a square. So what we have to do is multiply the electric field with the length over which it is valid and integrate for the entire range for which it is asked, and it divided by total length. Now this kind of average is done in every place. For example, if you have to calculate the average velocity, so let's say versus time, the velocity is varying, and velocity is varying like v is equal to v naught t square by 5. So what, and but this time we have to calculate the time average of the velocity. So what we'll do is this entire time, let's say it is asked that we have to find out the average velocity between 2 seconds to 5 seconds. This entire time or 2 seconds to 5 seconds, we'll divide it into small parts, and we'll take one such time at some time t. We'll take this small time element dt. This time element dt is taken at t time from the beginning. From the beginning means from this 0 point. So from this 0, let's say t time has already passed. In the next dt time, what is the velocity? So what is the velocity at this t time? This. Multiply the velocity with the time for which that velocity is valid. Integrate it for the entire range of time for which it is asked and divided by the time duration. So this is how we calculate the average value of velocity. So this here t is the we can say the variable with respect to which we have to find out the average. In this case, we have to find out the average of electric field with respect to x. So that's why we integrated with respect to dx, and here we integrated with respect to t. Now why do we multiply the electric field here with the distance for which it is valid, or why do we multiply the velocity with the time for which it is valid? So this comes from basic definition of averages. Let me tell you a little bit about the average here, basic definition. Let's say one person lives for 20 years, second person lives for 30 years, and the third person lives for 40 years. And if I ask what is the average life, we will say 20 plus 30 plus 40 by 3. That's it. But if I say that the 5 people have a life of 20, 10 people have a life of 30, and 6 people have a life of 40. And if I ask then what is the average life, so here just like you are adding all the lives and dividing it by the total number of lives, here also we need to add all the lives. Now this 20 of life is for 5 people. So 20 life is for 5 times. So we can say 20 into 5. Similarly 30 into 10 and 40 into 6 divided by total number of people or total lives, which is 21. So what we do is we multiply the life with the number of people for which that life is valid. Then multiply the life with the number of people for which that life is there. So here also we multiply the electric field with the distance for which that electric field is valid. And then next, this electric field also multiply the electric field with the distance for which it is valid. Because the electric field is continuously changing, the electric field is valid for dx amount only or dx length only. So electric field multiplied by the distance for which it is valid, integrated and divided by the total distance 2a. Now this will be considered as electric field average over a line. But here it is asked from us in this question to calculate the electric field average over an area. So what do we do in this case? Let's say we have an area, flat or curved doesn't matter. We divide it into small parts. Now let's take one such a small part here, dA. Let's say at this location electric field is like this. So multiply the electric field with the area for which it is valid. Then take another dA here. Let's call it as dA2. There the electric field is E2. So multiply the electric field with the area for which it is valid. Keep doing it for all the dA and divide it by the sum of all the dA. Sum of all the dA is total A. Now here an important point is this is not the flux. Someone will think that okay, electric field into area is a flux. But actually in the flux we have area as area vector and there is a dot product. And the outcome, this flux, is a scalar quantity. Here the area is not the vector, here area is this geometrical area, the scalar. And the outcome is a vector. So this will give you the electric field averaged over the entire area. Now that we know how to calculate the electric field average over an area, let us see how to solve this question. So first we'll take the charge to be outside, then we'll take the charge to be inside. So what is its average electric field over the entire surface? Now let's say the charge is here at a distance of r from the center and the radius of this sphere is r, or we can take it as a. Now let's say we take a tiny area dA. So what is the electric field that this charge, point charge, is creating at this location? So that electric field will be in this direction, and that electric field will be this, let's call it as E vector. Now if you take another element on the opposite side, this dA, it will also get some electric field in its area, and that electric field will be in this direction. So we have to multiply this electric field with this area and this electric field with this area. So this electric field, let's say, is inclined at an angle theta. So electric field into this area will be like this. And when we talk about this one, here the electric field is like this. So electric field into area. Now both of these areas are symmetrical with respect to this horizontal line. Now this EA, we have to add it up for all the elements. But while adding this electric field into area and electric field into area, what you will observe is that for this vector and for this vector, the upward and downward component cancel out, only the leftward component will add up. So overall it will be E cos theta, the horizontal component, into dA only we need to integrate. So ultimately it will boil down to E cos theta into dA. Integration of this. What is theta? Theta is the angle which the electric field is making with the horizontal. Now this we need to sum it up for all these dAs which make up the sphere. Now how to this do this kind of an integration? Actually, we don't have to do the integration. I'll tell you why. Let us say in this dA area there was a charge of charge density sigma. So how much force it will get from this Q? So for the force that this dA will get is electric field, whatever is the electric field this Q is creating, multiplied by the charge. And in this dA area I'm assuming the charge density to be sigma. So charge density into area is the charge into E is the electric field. So that's the force which this sigma dA will get from the electric field in this direction. Now if we take another element here with the same charge density sigma, how much force it will get? Same force magnitude but in this direction. So when we calculate the net force, we have to sum up only the horizontal components. So horizontal component will be E cos theta into sigma dA integration. So this is the horizontal component of force which this entire thing will get from this Q. This entire thing will get from this Q. Now let's take sigma out and write E cos theta into dA. Now if you see, this is what is E average and this is what we have to find out. This E average, E cos theta into dA. So we can write that the force horizontal component on this overall all the sphere elements put together, the integration, so that so this force will be sigma into E average. So what will be the E average? E average will be equal to electric field into area. But as I told you that if we take area here and if we take area here, charge is here, this electric field into area and this electric field into this area. So when you do the electric field into dA for this and electric field into dA for this and add it up, then their horizontal components will only add up, vertical component will cancel out. So basically we have to integrate only the horizontal component E cos theta into dA. Integrate. So instead of taking the total electric field, we can very well take only this horizontal component, because vertical component will anyway automatically cancel when we sum up all the EDA's values. Now this numerator, which is the sum of EDA, will is this, and that you divided by the total area. So what do we get here? And this is just the E average magnitude. So E average is equal to integration of E cos theta dA divided by the total area, which is 4 pi into radius square. Now what is the radius taken here? Radius taken is, let's say the radius of this sphere is R. Actually capital R will take it. So we can say that integration of E cos theta into dA is equal to 4 pi R square into E average. Now we have to calculate this E average, so we have to do this integration. Now what is this integration of E cos theta dA? This integration. So this integration is equal to 4 pi R square into E average. So this becomes 4 pi R square into E average. Now this is the total force on this sphere from this Q. But the force that the sphere gets from the Q also will have the same magnitude as the force that the Q gets from the sphere. And how much force this Q will get from this sphere? So Q will get a force from the sphere. So sphere will exert a force as if it's a point charge. So entire charge of the sphere, you can put it at the center. Total charge, whatever this Q is. So that will be equal to 1 by 4 pi epsilon naught into Q by R square. Now what is this Q, the total charge on the sphere, that you can write it in terms of charge density. In fact, this entire thing is charge density only. So this charge density and this charge density will cancel out. So we get Q is equal to 4 pi r square into E average. Actually, the charge density is Q into Q divided by 4 pi r square. So Q by epsilon naught will remain. So E average is equal to Q by epsilon naught into 4 pi r square. This is the average value of electric field at the location of the sphere. Now, what if we have a point charge inside? And let's say that the point charge here at Q. This is a point charge. Now, how much average electric field it creates everywhere? So here, uh, electric fields will cancel out when you take average. Why am I telling you like this? What is the reason behind this? Let's say we take this dA area. There it creates this Q creates an electric field in this way. But if you take this dA area, there the electric field is like this. If you take this dA area, here the electric field is like this. If you take this dA area, here the electric field is like this. So this electric field into dA if you do, and this electric field into dA if you do, and this electric field into dA if you do, and this electric field into dA if you do. So one E like this, one E like this, one E like this, one E like this. It's like they are kind of in different directions. So it's like the good probability that the average value of electric field will come out to be 0. In fact, it will be 0 and we'll prove it. So let's start. Again, the same logic that if the charge here is Q, then only we are interested in the horizontal force, because if we take one D element here and another D element here, this dA element will get a force in this way, provided there is a sigma here, and sigma will let us assume everywhere. And this dA will also get the force like this, and force will be electric field E into the charge sigma dA. Here also electric field into the charge sigma dA, and let us assume sigma is present everywhere. Now one force on this element like this, one force on this element like this. Finally, we are interested only in the horizontal component. So let's say this angle is theta. So what is the horizontal component of the force E sigma dA cos theta? E sigma dA cos theta. And let us integrate this. So we get sigma into integration of E dA cos theta. So this is the force which this point charge applies on all this put together. We have to add E dA cos theta. Now whatever force this charge applies on this entire sphere, same force the entire sphere also applies on the charge. But a shell's property is that a uniformly charged shell has a property that at any point inside it, its electric field is 0, which means if you keep any 1 coulomb here, it will get 0 force. If 1 coulomb gets 0 force, Q also gets 0 force. So the force that Q will get from the shell is 0. So the force that Q can exert on the shell is also 0 by Newton's third law. So this force will be 0. So integration of E dA cos theta is 0. Now what about the electric field average value? So if the electric field here is E and here the electric field is like this E, so this E here is valid for dA area. This electric field E is also valid for dA area. When you take the average, you have to sum up all this EDA and divide it by total area. Summing up all the EDA is like integrating and dividing it by the total area. This is what is the E average. Now you know that this E average will come out to be in horizontal direction only, because one E like this and one E like this, so net E like in the horizontal direction only, overall like terms will get added. So we can very well write it as E cos theta. So multiply E cos theta with the area for which it is valid, sum it up for all the areas, divided by the total area. This will give the average value. Now we know that this integration is 0 if the point charge is inside. So this integration is also 0. So E average is 0. Which means if the charge is kept here, then the average value of electric field that it creates on the sphere is 0. And if the same point charge is outside, then the electric field that it creates over this entire sphere area is kq by r square. So this is the answer. Let me know if you have any doubt. Thank you very much.